Okay. Okay, so welcome to the CPPC seminar. So today it's a pleasure to have Ranjan from the Center of High Energy Physics at IISc. So Ranjan and I were classmates during our undergrad days in Presidency College in India. And he did his PhD with John Beacom at Ohio State, then moved to Stanford for a postdoc, then in Germany at Mainz for a postdoc, then at CERN, and finally joined as an assistant professor at the Center for High Energy Physics. And he mostly works on astroparticle physics, mostly early universe cosmology, as well as beyond standard model searches. So yeah, so take it over.
Okay, all right. So thank you everybody for coming. Thank you for the invitation to the 1 and 1. So this is part of a joint grant that we have. Since I anticipated this is the Sydney Consortium for Particle Physics and Cosmology, I tried to, and I knew that there would be a lot of expertise in the audience. I'm trying to give a talk which will probably be useful to people who are interested in cosmology and also people who are interested more in particle physics. Hopefully, if you have any questions at any point, please feel free to stop, ask, and I'll be happy to answer. And this also has a lot of astrophysics, astronomy, astrophysics. Okay, so I don't have my mouse. So I can't point.
Do you have a stick?
I thought there was a stick here.
There is a stick somewhere.
Yeah, maybe I can stand.
Yeah, maybe just stand
Yes.
if you don't.
No, that is even better.
I mean, I think they're doing a lot of stuff here.
Okay, I can just point my hand. And just fine. I have to just run around a bit. Yeah, as long as you're not. Okay, so this work obviously is not done. So I'll be presenting two different works. So obviously these were done in a collaboration of various people. One of whom Taluk is here. He's a postdoc at Sydney. And then Akash Kumar Saha, Thashin Krishna, Ranjan Sherpa are my students. Priyank Parashari is a former postdoc, and Nirmal Raj is a faculty member at IISc. If you have any questions, feel free to stop and ask me, and I'll be happy to answer. All right. So as I said, I'll be talking about two different things. The first work I'll be talking about is how do you probe the primordial power spectrum using JWST observations. Some of these words are uncommon to you. I'll explain what these are. And in the second part, I'll be talking about how do you search for. So this is a work that has already been published. And the second part of the talk will be something that we will put out in archive really this week. We are already late. Searching for dark matter electron scattering using high energy neutrino observations. And I'll explain what these are. And if you're unfamiliar, I'll try to explain what these are. Okay, so the first part is probing the primordial power spectrum using JWST observations. Okay, so many of you, or maybe all of you, may be familiar with this picture of the cosmology. All right, so this is sort of like the history of the universe. It starts with the inflation/Big Bang. There was the CMB recombination. CMB was formed at this time. There was a neutral medium. The first stars formed. It ionized from galaxies, and we are somewhere here. So this is the sort of brief history of the universe. And this has obviously been confirmed by various observations, for example, by the Planck. And if you see in this thing, there are some parts of this picture which we know very precisely. Obviously, we know redshift 0 quite well, right? Obviously, we know CMB extremely well, right? These plots are kind of CMB. But if you look at it carefully, there are quite a few question marks in this plot, and these are parts which we do not know of, right? And as I'll say, JWST is already shedding some light on it, and we'll see how we can do some new physics with that. And I'll go on as we go. All right. So, in a more quantitative manner, the entire plot, like this plot, can be explained by the 6-parameter lambda CDM cosmology. I've taken these numbers from the particle data group, and as you can see, these numbers are extremely precise. So, one question you can ask, both as an astrophysicist or cosmologist or a particle physicist, is how do we probe these numbers more precisely, or can we probe the lambda CDM cosmology in parts of the parameter space which has not yet been probed, or can we answer outstanding questions about it, right? So we will basically try to do this thing, the newer regime thing. Can we probe lambda CDM cosmology in a part of the length scale which has not yet been probed, but which JWST is actually probing? So again, let's look at this picture. As I said, there are a lot of question marks. In fact, funnily, JWST is actually trying to answer all those question marks. If you're a bit careful, right? So first task, JWST maybe is probably having a hint. Reionization, JWST is already having a hint, like what is causing it. At least he has ruled out AGNs. There was some recent paper, and maybe this one 21 centimeter, obviously JWST cannot do it, but there are experiments in Australia which is trying to search for 21 centimeters. And then the first galaxy again, JWST is probably getting a hint of it. Right? So this part of the parameter space, or this part of the timeline of the universe, is not known at all. Literally don't know anything about it. In fact, before 2022, we literally did not know anything about it. We had effectively no data in some sense. Right? So there was some data, and I'm just sort of saying it in a colloquial manner, but there was some data, but there was not much known. And JWST has really started a revolution in this field. Right? So one of the things that we got started with was JWST has been discovering the earliest galaxies that are observed, and can we answer fundamental questions about particle physics, astrophysics, cosmology using these galaxies? So that's the main question. JWST is discovering, as I said, the earliest galaxies as observed. I'll come to the redshift to tell you some numbers more precisely. Can we answer very fundamental questions of the universe using those? Right. Is that clear? Any questions? All right. So why JWST? Well, there are a lot of astronomers, obviously people will know it better than me, but if you have studied Astronomy 101, the first course that tells you that young stars are obviously hot, right? Stars are forever cooling, right? They're born hot and they're cooling. They emit in the UV light, right? So this is a plot taken from some 101 class. Sorry, the resolution is a bit bad, but I don't know. It's probably the computers are not talking to each other properly. So this is the wavelength of the x-axis, and this is relative intensity. A star which is born at 15,000 Kelvin probably has this is the wavelength, assuming some black body, and as the star cools, it obviously becomes the wavelength becomes like this, right? So the star emits. Young stars, which imply hotter stars, emit mostly in the UV, right? So they have a continuum distribution, as you can see, but the peak is mostly at UV, right? So that's the main thing. And this is a cartoon that I have taken from either NASA or ESA website, which shows obviously when it's being born, it's emitting at UV. If it's far away, because of this redshift of space, expansion of space, there is a redshift. The wavelength gets stretched, and it will go to longer wavelengths, right? This emitted spectrum. If something is at redshift 10, and this was the record before JWST launched, there was this GNZ11 galaxy by HST. It was at redshift 10 point something. So obviously it gets shifted, and it's already HST. It was at the edge of what HST can observe. Right? So that's what redshift 10. But if it's at higher redshifts, redshift 11 or redshift 12, this was clearly beyond the range of wavelengths which Hubble Space Telescope HST could observe. Right? And this is what tells you that we need infrared telescopes to observe the highest redshift galaxies. Right? And this was one of the main science cases of JWST. Right? And again, there are people in Australia. One of the main things that I'll talk about who have actually worked on these JWST high redshift galaxies. Maybe I've already heard talks from them to actually discover these things. All right. So this is the electromagnetic spectrum. So the galaxies that we'll be talking about are HST, Hubble Space Telescope. It's mostly the optical. There's some IR coverage. JWST, that's the big one. You can just see the size is huge, right? And then there's Spitzer, which is definitely in the infrared, but it's much smaller, right? So just to give you a scale, so these are the size of mirrors. For a particle phasist, the larger the mirror, the more photons you observe, right? So it's the smaller flux you see. So this is Spitzer. The mirror is I think diameter is 0.85 meters. This is Hubble. This is Spitzer is mostly in IR, right? So Spitzer had seen some high redshift galaxies, but because of the small size of the mirror, they did not go very far. They could not see lower fluxes, right? This is Hubble. For Hubble, the radius or the diameter, I think this is the radius as far as I remember, is 2.4 meters. And this is JWST. You can see the size. This is 6.6 meters. First of all, it's in the IR band. That means it will see higher redshift. And then the mirror size is bigger. So it's collecting more photons. So it will see dimmer and dimmer galaxies, right? Because they're far away, they'll be dimmer, right? 1 over r squared, in a cosmological way. right? So JWST, when you may have seen, it was launched on Christmas Day 2021. It is in the L2 point. This is the Sun, Earth, Moon, L2 point. This is a picture of the JWST, and there are 4 instruments on board. NIRSpec, that's near infrared spectrograph. NIRCam, that's near infrared camera. MIDI, that's mid-infrared instrument, and NIRIS, near infrared imager and slitless spectrograph. So so as far as I know, most of the galaxies are discovered using NIRCam. NIRCam is like a camera; it just takes a picture, right? They're confirmed using NIRSpec. So this is spectrograph. So it takes the spectra, takes the atomic lines, and then it gives the exact distance, right? And confirms that it is a galaxy and not some AGN. Right? So that's a frequent confusion people have got into, like whether it's an AGN or it's a galaxy. And then MIDI has also been used, but I have not studied some of the MIDI papers, so I'm not very familiar. NIRIS I've really not studied. And these are 2 pictures, which I've obviously taken it from the internet, which tells you how clear James Webb JWST is, right? So this is the same part of the sky which Hubble looked at, and this is what Webb looked at. You can see it's a clear difference, right? Similarly, same part of the sky looked at by Spitzer in a certain band. The same part of the sky looked at by JWST MIDI instrument in a very similar-ish wavelength. Like this is 8.8 micrometers, and this is 7.7 micrometers. And you can clearly see the importance of JWST in looking at these early galaxies. Right? I mean, JWST has been doing other things also, right, for exoplanets and things like that. But in this talk, we'll be talking about what JWST can do with early galaxies. Right? What's the physics? As a BSM physicist, beyond scientific physics, why will I try to do it? Right? Is this clear? Are there? All right. So these are the plots. So they are busy plots, but let me take you one by one. It's actually once you understand one plot, the other plots are simple. Right? So these are some compilations. Last year, there is a more updated compilation, but it's not as clear. So that's why I just have this of the earliest galaxies. So the x-axis is the UV magnitude. For a particle physicist, it just tells you what is the UV flux. For an astronomer, you know it better than me, right? So this more negative means it's brighter, right? This is dimmer, right? And this the y-axis is the UV luminosity function. That means the number of galaxies per unit volume per unit wavelength, or actually technically per unit magnitude, more precisely. But again, as I said, I'm trying to sort of put it in a way which, as a particle physicist, also you understand. Right? This is like, as a particle physicist, is d2n d lambda dv. Yeah, there's things we have to learn while doing these things. And these are the data points, right? So let's look at the data points carefully. Those blue dots that you see, so these are from JWST, and these have spec-Z. Spec-Z means these are spectroscopically confirmed. So that means we have seen the spectra. These are guaranteed to be galaxies. I mean, as far as they're almost guaranteed to be galaxies. These colored, this is probably gray, are JWST photo-Z. Photo-Z means photometric redshift. That means, again, you take a picture and then you estimate, not from the spectra, just from the light curve, the SED, what is the spectrum, right? But you estimate it. It's not guaranteed that it's a galaxy. Plus some pre-JWST. Pre-JWST is mostly Hubble, and there's some Spitzer here. I think this does not have Spitzer, but this is mostly Hubble. All right. All right. So the way people do these things, as I said, before this, we had found the highest redshift galaxy, confirmed galaxy by Hubble at redshift 10. So what we do here is we have this data. We first plot these data points, and then we benchmark our cosmology to that. So what do I mean by benchmark our cosmology? More precisely, I would say benchmark our galaxy formation physics. The cosmology is obviously extremely well known, but what we do not know, but all of this is telling you, as it becomes clearer as I go on, is telling you how much light is being emitted. But cosmology tells you technically how much dark matter there is. Right? So there is a conversion factor which we'll come to, and this is actually one of the main things that's happening in the astronomy community about JWST. I have some reference. I'll talk about it. So they have benchmarked it, right? So it depends on, for example, something called sigma UV. Sigma UV tells you for a given mass of the dark matter halo, you can convert that to some light in the UV thing, and sigma tells you what is the spread. That you take a Gaussian and take the spread. What is the spread of it, right? So people have benchmarked it at redshift 10, right? So because they say we understand the galaxies, and then what you do is you measure it at redshift 12, 14, and 16. They are only photometric as far as I know, photometric conformations, but 14 we definitely have spectroscopic conformation. We have the highest redshift galaxy which JWST has seen is at redshift 14, 13 point something.
So what is the level of, because I have heard people arguing about this, about the spectrographic, so what is the level of confirmation,
So
what's the confidence level?
So colleagues can answer. As far as I know from archive, if you take a spectra, you're guaranteed that it's a galaxy and it's not an AGN. But maybe somebody,
Okay.
Is that correct?
There's galaxies here.
Yeah.
There's a lot of technical detail.
Yeah, but if you take spectra, yeah.
To argue about it.
Yeah, but if you take spectra, you're almost guaranteed it's a galaxy. Is that correct? Almost, if I put the word. Or you're not happy with that also?
It's fine.
Okay.
Spectroscopic redshifts are very useful.
Yeah. Okay. Yeah. So, but yes, so there have been confusions. So there have been confusions. One is using the photometrics. So there was initially a galaxy which was at redshift 14, and after spectra it became redshift 5. So that is one thing. So because photometry, think of it like as a particle physicist, think of it like you're taking camera picture using a camera, but then you don't know if there's a dust in front of the thing, right? So that you're effectively measuring the intensity, the way I understand it. Spectra gets rid of it. But yeah, I have seen something, but again, as far as I know, it's probably mostly confirmed that these are the, all right. So here I have sort of given some of the recent compilations. I mean, it started from the first early ones. As I said, there are papers by Australian people. Some of the major discoveries are from people in Australia. So the early JWST data revealed several high-redshift galaxy candidates. As I said, initially, you only do photometry because you just take a picture and you do it. That's easiest. And then you have to do spectra because you have to zoom in on a, not zoom in, you have to concentrate on a source and you take the spectra. That is more expensive, all right? And after the spectra, as far as I understand, you typically can tell whether it's a galaxy or an AGN, right? The problem is here, all right? So this plot shows it. So you see these dashed lines. So this is the benchmark, right? So this dash. So what this says is I take this thing at redshift 10 and then I extrapolate it using the same cosmology to redshift 12, 14, and 16. Let's ignore the 16 for now because all of these are spectra, so probably it does. Sorry, all of these are photometric, does not matter. But let's do here. So you can clearly see here, for example, the dashed lines are, well, okay, within the error bars is probably fine, are probably away from what you expect from what the data is, right? The data is, say, for example, say this point, data is here, the dashed line is here, right? In this work, these people, Shane et al., including some astrophysicists like Mike Colchin was there, they were trying to use the early dark energy model, trying to say that will accelerate galaxy formation, and they were trying to say that, see, this is probably a hint of early dark energy, all right? Note that it's not, I should say that the fact that there is a discrepancy between the data here and the extrapolation from Hubble does not require BSM physics. In fact, there is this papers coming out. Even today, we have papers by this Thisan Zoom collaboration. These are galaxy formation collaboration people who have actually explicitly said that if you increase star formation and maybe also decrease a bit of dust in those galaxies, you can explain those things. So there are standard. So there, what I would say, there are standard model explanations of these galaxies. Why are they so bright and why are they so numerous?
So I actually read a recent article. So they're saying if you really confirm the 16,
yes,
that standard explanation will break
good,
down.
because Thisan Zoom, yes, I was going to say that Thisan Zoom goes. So it depends on which box you see. I think the highest redshift box I've seen is 13. But these papers are coming. Literally today, the third paper on Astropage archive is that. So yeah, so you may be right. So, but I think this, as far as I know, 16 there is no confirmation. At least there is no public confirmation. I am not aware of it. 13.9 or 13.6 or 7. It's really approximately 14. So these two. Okay. Yeah, but 16 may be in trouble, but we don't know. Anyways, so the bottom line is that so there are astrophysical explanations of it, right? I'm not trying to say although I'm giving the talk as a BSM physicist, I'm not trying to say that there are no astrophysical explanations. There are astrophysical explanations of it. But some of these astrophysical explanations were not anticipated, at least before the JWST discovery. This, I think, is a fair statement to say. Right? All right. Is this clear? Okay. All right. So I'll give you one plot which tells you how weird the problem is. But if just hold on, the first question is that how do such massive galaxies form so early in the universe? Right? This is roughly 300 mega years after the Big Bang. And the main thing that we are trying to do is, can we test lambda-CDM cosmology using this, right? Note that galaxy formation as many of you know, or maybe all of you know, involves n-body dynamics using large cosmological simulations. Certainly something which I don't have access to, but we were trying to use some semi-numerical approaches to approach this problem, especially, as I said, testing fundamental parameters of lambda CDM cosmology. All right, so the semi-analytical thing which we do is something that's there in textbooks. You can look at your favorite textbook, cosmology textbook, is called the Press-Schechter formalism. Press-Schechter formalism tells you, statistically speaking, so remember, galaxy formation is an n-body physics, it's a stochastic physics. You can't do it one by one, but you can do it statistically. Statistically speaking, what is the number density of dark matter halos given by d small n by dm? Here it is given d log, right, at a given redshift in a statistical manner, right? So that's what the Press-Schechter formalism does. And what we did is we tried to use this. We knew there were pitfalls there, and we were careful in the work trying to say that these are the pitfalls of this thing. But even then, we try to use this to say what can we do about this JWST galaxies, what new can we? And almost the entirety of lambda CDM cosmology is hidden in this thing called sigma, which is the mass variance, and that's very hidden. Right? The pitfalls are, so remember, galaxy formation is n-body dynamics. There is no analytical solution to it. What you have to do, this is a semi-analytical solution, but you have to calibrate it to some experiment. So, we calibrate it with some numerical simulation. So that's where these fitting functions come in. So famous, for example, the Shed-Torment fitting function, if you have heard, right? At that point when we were doing it, we did not have any access, and actually nobody had done it. Not that one. We were just saying that, well, let's just see what happens with this. That was our approach, right? Because we could do it semi-analytically. That's the advantage. And as I said, only now the numerical simulations are coming in, and that too including hydro. Here you require hydro because what you're seeing is the light, right? Not the dark matter. You're seeing the light. Anyways, so there are a lot of details here. Like how do you calculate the mass variance? So this is a standard formula, but the important thing is this depends on the power spectrum. Again, there are experts in this room, which actually this power spectrum P of k depends on something called the primordial power spectrum. This is something which comes from inflation, right? Some high scale physics, inflation is giving the primordial power spectrum times the t squared k. T squared k tells you, technically speaking, how do the modes evolve as their subhorizon in some sense, right? Basically, I mean, inflation gives you something, in case it's a bit technical for you. Inflation gives you this part, and T of k tells you how does it evolve at various rates, as the universe expands and things like that. That's in a very simple way. The primordial power spectrum has a form like this, given by the Hardy-Stanzelowitz spectrum, except that the NS is almost close to 1. Right? So this is, again, people say this is one of the hints that inflation is correct, but let's not worry about it. Bottom line is you can use this and calculate. So this thing is cutting off, not here, but here, but anyways, doesn't matter. So what is plotted on the x-axis is the dark matter halo mass. So this M that I showed previously, the previous slide, this M is the dark matter halo mass. Right? So that is important. Is the dark matter halo mass on the x-axis, and y-axis is the dm, number of halos per unit mass, right? In appropriate units, taking some value of a cosmological parameter, you can see for lambda CDM for z equal to 10, we have this line, the black line, and for z equal to 0, we have this line. So this plot clearly shows the bottom-up formation of lambda CDM. The heavier halos are formed much later. Right? For example, at redshift 10, there are no 10 power 13 solar mass halos, but at redshift 0, there are. This is an easy way to do it. All right. So note that this Press-Schechter formalism also gives you this dn as a function of z, and that's what we were exploiting. Right? This is the thing. We are exploiting this thing, right? To find out. So the point is that we are measuring very heavy halos at high redshifts. Can we use this formalism again? Let's say to probe the primordial power spectrum. This is what we were targeting in that sense. Right? You can also do other things which some of my students are doing. For example, there can also be new physics hidden in the t square, in the transfer function. And that also you can do. So as I said, some of my students are doing it. But in this work, we are saying how can we probe the primordial power spectrum? Because this, there is a proportion of this directly affects this thing. Right? I'll show you one plot which will be obvious. All right. So this is a compilation of the primordial power spectrum from this Gilman et al. So what tells you on the x-axis is the K, is the inverse length scale, which corresponds to some halo mass, okay? And this is the power spectrum, right? So this line is the P of K. This line is from lambda CDM, right? And there are various constraints from CMB, from DES, from Lyman alpha. This work was actually trying to use strong lensing basically they were looking at some quasars. This is the paper by Daniel Gilman. That they are looking at some quasars and looking at lensing and trying to probe the primordial power spectrum, right? So what they said is that, so this line, this central line is the lambda CDM. They said that it cannot go beyond this this two black lines, right? And these dashed were the priors in their analysis. Right? So they say that it cannot go, suddenly it can't be like this. It has to be within this band. And our aim was to see, can we actually do something better than this? That was our aim, right? Is this clear? Right? And as I said, these things will give you what is the halo mass. All right. So how do you do it? So if you look at the inflation literature, there's at least one model coming out every day, right? It's maybe like that. That's because it's a bit. Sorry, what? Yeah, it's like dark matter. Yeah, it's like dark matter. Yeah, it's like dark matter. The problem is not the model. The problem is to find the right model. So what we try to do is we try to do a model independent modification to the primordial power spectrum. Remember, the primordial power spectrum was k to the power ns. So what we did, so let's, instead of these equations, you can look at this plot. Again, k is on the x-axis. This is the power spectrum y-axis. Lambda CDM is this black line. We either do a blue tilt, that means goes up, or a red tilt, it goes down. Right? So these are things which can be predicted, which are predicted in various modifications of the lambda CDM. You can also have the running of the coupling. You can do various things, but we just did a very simple.
Running of which coupling?
The NS.
Oh,
this is even Planck constraints. Officially, Planck has a constraint of the D log NS D log or something like that, DNS D log, something like that. Right? You can do that, but anyways, we were just taking a hard cutoff just for a simplicity. So we have a cutoff. So there's a KP where the thing changes, and if it goes up, it's blue tilt. If it goes down, it's red tilt. As is obvious, intuitively, if it's blue tilt, you get more halos, more dark matter halos, right? So again, x-axis is the dark matter halo mass, d and dm. So the black line is lambda CDM. For blue tilt, you get more dark matter halos. So this is at redshift 0. And for red tilt, you get less dark matter halos. Right? Because it's proportional. Technically, it's not proportional, but anyways, this is what it is, right? Because you have more power, so that's why you produce more halos, right? And you not only produce more halos, you also produce more halos at an earlier time. So that was the basic trick that we were trying to use, right? And then this is just a mathematical expression that we were using, just putting a hard cutoff. So we have two free parameters. One is Kp, which is the favor scale, which tells you where we are putting this thing, and this Ms tells you whether this goes up or down with respect to the lambda CDM cosmology. All right. Well, it turns out that's a bit more complicated than this. JWST does not measure dark matter mass. What it measures is just light. More precisely, what it measures is actually the UV light. Right? At least when we were writing the paper, people were still using the stellar mass. Right? In fact, now people have realized that what people are doing in the initial part of using the stellar mass is a problem, because converting the stellar mass to UV light may not be. They were using the low rate shifting and just doing it. That may not be perfect. Right? Again, things have been, but as you will see in this whole talk, I'll be using m star, which is the stellar mass, simply because that's what the initial papers were doing. But if you're doing it, that's what, right? But I think the basic idea still holds. All right. So suppose we have a dark matter halo mass m. No. There's not a factor of 5. There's an important thing which this is in this slide. Okay. Yeah, this is the whole thing why Kisan Zoom project is going on.
So it's not a blank factor 5.
Oh no. That's what it is. That's what will mess things up. That's what the whole astrophysics is done. Right? So if you have a dark matter halo of mass m, what is the stellar mass m star? Well, first, as Deepan said, there's a factor of 5, right? Because if you are a redshift, the maximum amount of baryons is given by this cosmic fraction. You can't go more. You can't have more baryons than that, right? So you take that. That's the first thing. But that's not the thing. The point is you have to convert these baryons into stars. And how many stars are converted from a baryon is the unknown thing. And this is the problem. There is this epsilon, which is the star formation efficiency, which is completely unknown. So there are models in the literature which says that epsilon is 1. So these are called feedback-free galaxies. Like 100% baryons are converted to stars. And then there are models in the literature which says that epsilon is actually extremely Z-dependent and it's bursty. So when JWST is seeing these galaxies, these are at the bursty phase. Right? They're just very bright flash, and you have taken a picture at that time. So there are various models, right, in the literature. So this is where, if you look at any galaxy formation simulation, this is where the fight is about this epsilon, right? But we are trying to do it now. So once you have this, so m star is epsilon, which tells you the star formation efficiency, times f of b, which is this ratio, times the dark matter halo mass. So this tells you in a simple way, what is the, for a given dark matter halo mass, what is the M star? All right. So now now it's easy. You sort of calculate the things that were at least were there present in the papers. First thing was the cumulative co-moving number density of dark matter halos with masses above a certain mass threshold. So that's just integral of d and dm, right? Above certain halo mass, and then also there was this cumulative co-moving mass density, this m d and dm integral. Right? So these are things that were provided by astronomers at the time from the papers that we were using. All right. And then again, you can connect, these things are still at the level of dark matter halo. You can connect them to the n star and rho star by using these formulas. That's what we did, right? That's where all the problem is, all the controversy is. All right, so let's talk about the first thing. So the first discovery, and this sort of tells you, is again, this was a discovery from Laha et al. I think it was in Swinburne, where they used this Sears survey, and they found that there are at least 6 galaxies with stellar masses greater than 10 per 10 solar mass with this redshift. So why is this important? Well, so this is what I've plotted, just to illustrate the thing. Redshift on the x-axis, y-axis is stellar mass. So I will leave the star for now. So this plot is taken from Laha et al. That's what they have, right? What I've plotted, so these are stellar masses on the x-axis, redshift on the y-axis. What I've plotted is the stellar mass of the Milky Way. That we know very precisely, that is this number, 6 times 10 per 10 solar mass. But that's at redshift 0, and that's this. And this is the stunning thing. At redshift 10, Laha et al. Was finding galaxies which have a stellar mass as high as the Milky Way. This should not happen. They're already as heavy as the Milky Way at redshift 10, right? Why? How? All of these things, right? Or are we missing something? Have we messed up things completely, right? As far as I know, some of them, or maybe all of them, at least high redshifts have been spectroscopically confirmed, right? Anyways, so this is again a plot from Laha et al., which was basically showing this. Again, the stellar mass on the x-axis, the cumulative rho star, so this is the m, d, and dm in terms of the star on the y-axis. This is what is expected from JWST and IRAC at various redshifts before the JWST discovery, and this is what they have. So this was the sort of the tension that Laha et al. Had. And again, as I said, let me remind you, people have solved this using standard physics, right? We will try to see what we can do with some beyond standard model physics, right? So the questions are obvious. I mean, how did these galaxies become so heavy? Right? At redshift 10, they are already at the Milky Way mass. Why? And how come they're so numerous in number, right? It's not just they're heavy, it's not just one of them, right? There are quite a few of them. So this tells you why are they so numerous in number. So that's the question. So what we realized, as if you know a bit of cosmology, it probably is a very trivial thing. Realize that if you give a slight blue tilt to the primordial power spectrum, you can, as I showed earlier, you can form more massive galaxies, and you can form them earlier. So then, in some of the early papers, they were saying that you may actually require epsilon, that is a star formation to be 100%. So we said that is not required. You don't require such extreme astrophysics to do it. So this plot explains it. So these two plots are similar, the left and right. Let me just explain the left one. Again, m star, the stellar mass on the x-axis, and this is the rho star. This is the cumulative stellar mass density. So again, m, d, and dm in terms of the stars on the y-axis. So this is the Laha et al. Result. This band that you see, lambda CDM with a star formation efficiency of 20%, which was sort of expected at that time. You see, it hardly goes through the result, right? And then, as I said, there were some solutions with using feedback-free galaxies where epsilon is 100%. That means all gases converted into stars. We have never seen that ever in our galaxy, or not just in our galaxy, or anything in any of the galaxies, as far as I know. So that will give a line like this, right? All baryons are converted into stars. So we see that easily explains this result, right? We said, okay, if you give a slight blue tilt, I'll give you some numbers. Even blue tilt with epsilon 0.2, which is expected in standard galaxy formation physics, can easily explain this result. That's what we should show, right? This is at redshift 9, this is at redshift 7.5. It says the same thing, right? And these are some parameters of the blue tilt that gives this, right?
You're not saying where the blue tilt.
We'll come there. There is a problem there. We'll come to that, right? This is a tricky problem, right? All right. So this is the thing, right? So remember, I had the pivot scale, I had the slope, and I mean this parameter space will explain it. So it turns out that's some which is fine, except that this thing is in tension. This is the very weird problem. All right. So let's show why this. So if you take some new physics parameter, which is barely explaining the JWST result, so you have the k on the x-axis and p of k on the y-axis. This black line is lambda CDM result. The Gilman et al., the band that I showed you from the lensing is these two lines. Blue tilt is this line. This line, blue tilt, is barely explaining the Lab et al. Result. And as you can clearly see, it's already in tension with, say, for example, this data point. This data point comes from the HST galaxy, HST galaxies. The galaxies that HST has discovered, and do the same thing. Use the primordial power. Use the whatever we did to convert it to power spectrum, and you get this. You see already there's a tension. And this is something we pointed out, that you see there may be a problem, right? You can do this, but there may be a problem. Even later on, the paper by Andrei Kraftsov and Ariana Decker, who showed that even Milky Way will create a problem. We actually have a line on this in our paper. The Milky Way may create a problem, and they actually did a much more detailed work than we just wrote a line. They said even Milky Way galaxies, the number count of Milky Way galaxies may create a problem for this, right, this solution. Anyways, it's probably still allowed. I don't know. I mean, it's a really complicated question, to be honest. Maybe it's not allowed. So after our work, so again, we were doing a semi-analytical approach. As I said, many of the things that we are taking, which were not confirmed, there was a group in Japan by Hirano and Yoshida. They actually did an n-body simulation, and they somehow, sort of magic in some sense, they showed that the results what we have matches with the n-body simulations. At least when that means the fitting functions that we are taking in pressure sector, those are matching with the n-body simulation. That's what they're saying. And then almost around the same time, there was a paper by Kamiokande, who actually also showed the same tension. That I mean explaining these bright galaxies in JWST is really tricky, because HST is also effectively probing the same length scale. Because you see that this is the HST, the last bin of HST, right? And this is what it is. And this paper by Kamiokande also came with the same conclusion. All right, is this clear? Any questions? All right.
I wanted to ask one question, like
Yes.
this way of parameterizing like the deviation of the primordial power spectrum.
Yes.
Is it standard or is it?
Okay, so this depends. For example, in the Kamiokande paper, they were taking a Gaussian bomb. We took a like this. So this really depends on model to model. I mean, we just took one model where we can choose. What is the answer?
Features.
Features, yeah. People also take a lot of scale-dependent features and things like that. I mean, as I said, there are many models. It's impossible to. We were just doing it in a manner which is probably useful.
I mean, in principle, you could have started with something flat on the top, and then just
You can do anything. In principle, you can do anything. For example, people do non-Gaussianities. Also, that will also introduce features in the primordial power spectrum. You can do things. Right? This is sort of like new physics. Anything can be done, but you say take whatever it is.
Breaking from slow roll.
Yeah.
Yeah, it could break from slow roll.
Yes. Correct. All right. Are there other questions? Okay, if not, let's move on. Let's move on to the next thing. So while we're doing this, there was another thing came up. Okay, this is also an old result. So this was from a different JWST survey called the JADES, JWST Advanced Deep Extragalactic Survey Program. So this was done by these people, Curtis Lake et al. And Robertson et al. So they discovered 4 galaxies at that point. Now there are many galaxies spectroscopically. These are at lower masses, so this is not a problem. And these are different redshift. They're actually technically at high redshift, not technically, they are at high redshift, but they are different masses. But the idea that they did is that they used these 4 galaxies, again, which are lighter, much lighter, and they compared it with various simulations. So these are the bunch of simulations, and they showed that at least these 4 galaxies are okay with simulations. All right. So again, m star on the x-axis, number density of galaxies on the y-axis. You see that these are some of the data points, and these bands that you see, these are coming from simulations. All right. And what they did, most importantly, is that they found 4 galaxies, one at redshift 10, 11, 12, 13, very precisely because they were using spectroscopy. And then what they said, this was done by Keller et al. What they did is they said that, well, we look at a patch of the sky, we have spectra, so we know the redshift range. So that means that defines the volume. We have found 4 galaxies. So the number density of galaxies must be greater than 4 divided by the volume. That's what they did. In a very complicated manner, that's what they did. They just did it, nothing more. So again, you see a patch of the sky, you see 4 galaxies, so the number density must be greater than that. I mean, greater than because it's not complete. That's why it's greater than that. That's the simplest thing that they did. All right. So they put upper limits on this, and then these, by the way, these data points were from spits around redshift 10. Anyways, so once we got this, then same work. We said, okay, now this tells you something interesting. Now this idea is obvious. If you remember the early plot, blue tilt was giving you more galaxies, red tilt was giving you less galaxies. So the moment you have a lower limit, tells you can't have too much of red tilt. Because again, it will be in contradictions immediately, right? So that's what we did. These are the 4 redshifts, precise redshifts. Again, m star on the x-axis, number density of galaxies on the y-axis, assuming some star formation efficiency. Note that the star formation efficiency here is an order of magnitude smaller. Why? It's just an environmental effect. We have no idea. We have a paragraph on it. We say we don't know what is happening. But the star formation efficiency required is an order of magnitude smaller. Maybe first of all, these are different galaxies. These are not the same galaxies that we are talking, right? So the fact that you have an upper limit here, what you can do is you can take the power spectrum and run it. And for example, see, if you have this, right, you will have this. Suppose you make a very hard red tilt, right? Obviously, that will not be allowed, right? Instead of this, suppose it just falls like this, falls like a rock. It will not be allowed, right? So that's what the idea what we were using. I mean, obviously we did a few numerical things, but that's the basic idea that you can't have too much of red tilt, right? Otherwise, you will not obey this lower limit. And remember, these are spectroscopic lower limits, so these are guaranteed to be galaxies. All right, that's we understood. So this is what we did. We did a lot of math, and this was our result. So again, k on the x-axis, pk on the y-axis. Black line is lambda CDM. This band is the Gilman-Etol band. These are the data points. Some of them are UVF. UVF is from the Hubble. Lyman alpha is from the Lyman alpha. And what we have is, depending on the k of p, remember this was the pivot scale where I do the red tilt or the red tilt here. You see these lines, so these are the lower limits. So that means the red tilt can be less than this. Right? So this was clearly better than, slightly better than Gilman-Etol. Gilman-Etol said cannot be lower than this. This dashed line, we went slightly better. Just to quantify this, so this is the delta pk, which is lambda CDM minus the red tilt by lambda CDM. This was Gilman-Etol, this line that you see, right? Again, as a function of k, right? And this is what we have for various kp's. You can see slightly more improved than Gilman-Etol, right? Just like coming from this first JWST data set. And the bottom line is that in this k range, between 2 to 7 megaparsec inverse, with the factor of h, as far as we know, these are the most stringent constraints on the red tilt in the primordial power spectrum at that point. Right now, I think we have more data, we can do this even better, right? But I think this is definitely the most stringent constraint on the red tilt. All right. Is this clear? Are there any questions?
Did you choose the pivot scale to be 2 or something?
Yeah. So then we do because then the change becomes too much. So this constraint depends on what is the pivot scale.
Yeah.
So that's why you see the color depends on it. So you have to be a bit careful. So this is the k range, not for the pivot scale, right? So there's
What is your pivot scale?
So this depends on.
Oh, right, okay, 1 and 2. I see.
Yeah. So the entire range between 1 and 2.
But if you have your pivot scale at 1 or 2, wouldn't it have a huge red tilt on very large scales?
No. So no. I mean, it starts roughly from here, right? 1 or 2. So it starts.
Yeah, but if I extend the same tilt and go to the
No. So
So
it's like this. I just put at this point below k of 1. It's not changing. Like if you look at the, let me go. This is the. So the way we are parameterizing. Yeah, exactly. It's a broken piecewise power line. Yeah, exactly. So it's only at this point.
Okay.
Below that there is no change. This is something that we just found it in the literature.
Okay, not the usual understanding of the tilt, which is not peaceful.
Yes, correct. Yeah, this was a bit different. I mean, and the reason we use it actually is the reason because there was at least one simulation we found which was actually using this n-body simulation. We could calibrate our redshift with this. So that's why we were using it.
If you go to scales larger than 0.2 inverse megaparsec, you have essentially 0 wiggle room with the tilt because the CMB completely misses the tilt of harmonic.
Yeah, but it's only because this is piecewise.
Yes.
Yeah, sure.
That's why you have to put the pivot scale
Yes.
at larger.
Correct. Yes. That's the nice way to put it. All right. Are there other questions? How much time do we have?
I mean, you would have to build I don't know, but probably you have to build a peculiar model to have a piecewise
So I think
spectrum.
we have seen
Your
it.
potential.
Yeah, I think we have seen it. There was
Yes, but that potential has to be probably weirdly shaped to it.
No, see, as I said, here you can also have a running of the cup of the NS. The same result which will hold. I mean, you have to do it see, this is like a BSM physics thing, right? It's technically like the result.
Simplified models thing.
Yeah, exactly. Technically, it will depend on what model you take, but even if you have a running spectral index, the same result must hold, right? I mean, quantitatively it can change, but the result must hold. You can't, for example, this plot, right? This plot, you cannot violate this law limit or whatever it is, right? Yeah. So that was the main idea. We had to take one model, we just took one model. That's it. But yeah, there are various models. As I said, I mean, the people who have taken Gaussian things, non-Gaussianity, and things like that. People are doing it. All right. Is this clear? Or
Can I ask one thing? So
Yes.
you mentioned before there was also an explanation in terms of standards astrophysics.
Right.
Which could explain it. So
Yes.
that means there's also a certain error bar associated with all of that.
Standard
Right?
astrophysics.
Standard astrophysics. How large is that error bar?
Okay, so I don't know, so maybe someone in the audience can tell it better. So let me tell you some of the solutions that I know of. One of them, as I said, is something called feedback-free galaxies. That means they're taking all the baryons and converting to stars. There are no gas in those galaxies. So those guys have dark matter and only stars. So galaxies like this
also be quite extreme.
Yes, we have never seen a galaxy like this ever. But there are people have proposed tests for it. Right. The other one is that these galaxies have less dust. Right? For some reason, I mean, I think less supernova or something like that. I don't remember exactly, or maybe supernova is driving out the dust. That's another thing. The other thing, which is this Tisan Zoom project, as far as I understand, reading it only for a day or two, is that they are saying the star formation is very bursty. So so this epsilon that I've shown is sort of like average. It's a theorist dream, right? As an average. But remember, you are taking the picture of the galaxy at one snapshot. Maybe at that point it was very high, and then it became quiet, so that it became and that's so these are called bursty galaxies. It's one of the titles is burst zoom, something like that. The first paper, and that's what they are saying. That maybe the star formation is really bursty, really stochastic, is really bright, and we have got those pictures. We have got those guys at when they are so bright. And then there's one thing. Obviously, there's an observational bias. Maybe these galaxies are bright. That's why we saw it. People have also done it. And there's also something which is more observational, is something called the extreme value statistics. I actually haven't yet understood that.
It's like quantum zero effect or something.
No, nothing to do with quantum. There's something to do with statistics.
No, it's statistics. Essentially,
You really push it, yes.
Like Poisson noise.
Yeah. And yeah, so I've already said 4 or 5. Yeah, so there's quite a few. So now if you ask what is the error bar on the standard astrophysics, I don't know. Astronomers, yeah, it's true, right?
I think would be interesting.
No, this is
kind of, right?
no, I agree. But the important thing is, I think all of these models, they have
So all of them
tests.
sounded quite extreme.
Yes. But I think all of them, actually, as far as I know, they have tests. Like, how do I test this thing? Like the bursty galaxies or the feedback-free galaxies or things like that. And I mean, we will see which one comes out with it. There are also some papers which say that maybe the calibration is wrong. At least for some of them. I think for most of them, the calibration is right. For almost all of them. But as far as there are 2 galaxies failed catastrophically. They were greater than redshift 10, they become redshift 4 or 5. That's a huge change. Yeah.
So, I think 10 minutes.
Okay.
So
I'm running a bit late.
no, we can continue afterwards. So, but like,
Okay.
we'll have to stop for the main audience.
Yes. Anyway, so this part I'm done. So are there more questions?
So, do you know what kind of models you can write down, or is there?
this?
Yeah.
No, we have references. We did not do it. Now we are actually more interested in actually going to the transfer function. So there are various BSM physics models which will change the transfer function, where you keep the primordial power spectrum as exactly as the lambda CDM. Don't change it for the transfer function, because technically what we measure is this P of k. We don't measure it separately, and then it depends on how you distinguish it. It's a more complicated question, but that's what we're doing. Yeah, models. I think. I mean, there are many people.
Sure.
Neil Weiner, Lian Tao, and they have been already started on this.
Okay.
On these things. Antonio Riotto, obviously.
Antonio Riotto.
Yeah, not Gaussian. Yeah, not. Yeah. So there are many models. I mean, new physics, there are many models. You can do a bit of primordial black holes. That will give a slight bump. That will be more in the blue tilt region, not red, because it's a bump. But anyways, so the models can be there. Many models in the market. That is, I think, not a.
Okay. Yeah.
For now, it's not a problem. We did not look at it. We just cited a few. That's it. All right. Are there other questions? Okay. If not, I don't know. I'm running late. Sorry about that. But let me talk about something else completely different. Right? All right. So we'll be talking about breaking the Lambda-CDM cosmology. Now let's talk of taking the standard model of particle physics. Right? Here searching for dark matter. All right. I don't need to tell the audience there is evidence of dark matter. You guys don't know it better than me. And then there's this famous diagram for the quantum magazine again. I'm sure you've seen it better than me. Know it better. So the important thing that I want to say, especially to the younger people in the audience, is that I think dark matter can have a wide mass range. So this is what is the candidate of dark matter? That's the question you're asking. Wide mass range. It can be as light as 10 power minus 21 electron volts, but it can be as heavy as a few tens of solar masses, and there can still be a substantial fraction of dark matter. Right. The bottom line, I think, in the search for dark matter, as we were discussing in the beginning of the talk, the problem is not is to find out what is the right model of dark matter, which is one, theoretically consistent, and two, which is which is well, we can get a signature of it. Right. So those are the important questions that we are trying to ask, and both of these things, the theory and the observation of this experiments, are important. All three of these things. So what we are trying to do now, that we should really post the paper in archive this week, we're late, is trying to search for dark matter electron scattering. So the idea here is, again, there are people in Australia working on these experiments, is that you go underground in a mine, you put your detector, you go in the mine so that you can get rid of various backgrounds, and you hope at some point dark matter will come in, will jiggle your detector, and you'll find that jiggle. That's the point. Now that jiggle can be either kicking a nucleus or kicking an electron. Here we're talking about dark matter electron scattering. Right? So as far as I know, this is the latest plot of dark matter electron scattering. X-axis is the dark matter mass, y-axis is the dark matter electron scattering cross section. Anything that you see shaded, except this benchmark model thing, is ruled out. Right? So anything above is ruled out by you see various names. So these are various names of experiments, right? And these are some models, all right? So they're showing that you're actually, as I said, you're trying to probe interesting models which are theoretically viable, right? So that's what this is for some particle physics parameters, right? For dark matter electron scattering, just like for dark matter proton scattering or dark matter neutron scattering, we have various target materials. We have silicon, the major ones are silicon, argon, and xenon, right? Then that is because depending on the detection technique, the silicon is most sensitive to lightest masses. So that's basically Damik and Sensei, this one. Sensei, Damik, this one. These are silicon. Then there's argon. So these are most sensitive, around 50 MeV. Most sensitive means the minimum. So this is dark side. The minimum you see is roughly 50 MeV. And then there's xenon. So these are the biggest experiments. So this is xenon 1 ton. This one here is most sensitive to 200 MeV. Right? So argon and xenon are actually very, very similar. But anyways, since they are various things, so these plots are made for standard standard astrophysical parameters. I mean, the most important thing being what is the dark matter velocity in the solar system. But again, Taruk has worked on a variety of things, how these limits will change if the dark matter velocity in the lab changes, or in the solar system, more specifically in the solar system changes because of various things. And there's something maybe because of earlier merger history of the Milky Way, for example. All right. So if you look at this plot, it's sort of obvious. Well, you can ask various questions. One question you can ask is, well, so this plot is going up to 1 GeV. What happens at higher masses? Why do they stop at 1 GeV? 1 GeV is not a special number, right? It's not a fundamental constant. Put it that way. Well, the reason is, at least for these constraints, these limits will just go as 1 over m chi, not to arbitrarily high masses, but at least they'll go over at least for a few more orders of magnitude. They just keep going as 1 over m chi, right? And that is simply because the dark matter density in the solar system is well known to 30% accuracy. This number 0.3 plus minus 0.1 GeV per cubic centimeter, but the mass is not known, so that the number density goes down as the dark matter particle gets heavier. The number density of dark matter is lower, right? Because the energy density is fixed, right? So the question we were trying to ask is, can we improve this? Can we improve these limits at heavier masses? That's the question. Yes.
How is that number determined?
This one.
Yeah, is that a velocity dispersion of the disk kind of argument?
No. This one. No. So this one is determined by. So what you do, for example, the latest measurements are from Gaia. So you look at stars which are near the solar system, and you look at their motion, and they very accurately account for the baryons, that we including the stars and the gas, and remaining whatever mass is there, you put it in this.
Okay, thanks.
That's it. Yeah. So there is 30% accuracy. So the question is, how do you do better sensitivity from these plots, right? So that's obvious, right? So well, you build bigger, better detectors. That part is obvious. And just to give you a sense of some scale, well, dark side, which is the argon experiment, has this exposure. Exposure here is volume times the time of running, right? So 12,000 kilogram days. Sensei, this is the silicon experiment. This has 500 gram days. Damichem is a smaller one, 85 gram days, and xenon N10 has some 22 ton days. That's the exposure. Can you do better, right? The answer is yes, and this is a very old idea. I mean, people in Australia have worked on it. Is using the sun. Well, if you think about it, the sun as a dark matter detector has orders of magnitude large exposure. Remember, I defined the exposure as the volume times the lifetime. Right. Well, the sun is living for 4.6 gigayears. The sun's mass is 1 solar mass. Right. So this is the exposure. You can see this is orders and orders of magnitude larger than what we can do in the lab. So maybe, and this is what people have done, at least for dark matter proton scattering extensively, we can use the sun as a dark matter detector. Right. And this is what we do. We use the sun to probe dark matter electron scattering. Okay, so what's the basic idea? Since I don't have time, I'll just try to briefly say. The idea is actually super simple, right? The idea is, this is some cartoon of the sun. Very far away, there's a dark matter particle. The dark matter particle gets attracted gravitationally. And then as it's going through the sun, if it has a non-zero dark matter electron scattering cross-section, so this is not a gravitational cross-section, this is a particle physics cross-section, due to some new physics, it can scatter with the electrons and lose the energy and get captured inside the sun. Right? So as I said, this is an old idea. Many people have worked on it, but I think the dark matter electron scattering part has not received much attention. So note that only a small fraction of dark matter particles will scatter with the electrons, and even smaller fraction will scatter such that their final velocity is less than the escape velocity, such that they get captured inside the sun. Right? Anything to get captured, it must be less than the escape velocity. That's straightforward. Right? So there's a complicated formula for this. Let's ignore this. This is all of these effects. This depends on total number of electrons that are there in the sun. Depends on the number density of dark matter. What is the flux of dark matter, and what is the capture probability? And obviously depends on dark matter electron scattering. That's where the particle physics comes in. Right? So these are all the things I've said. Again, many people have worked on it. So just to give you a scale, some sense of numbers. If dark matter has a mass of 100 GeV, and it has a dark matter electron scattering of something like 10 power minus 39 centimeters squared, which is not yet ruled out, you can have a huge amount of dark matter inside the sun. This number, so this is some number, but this is equivalent to some mass of asteroids. So for currently allowed dark matter parameter space, there can be an asteroid amount of dark matter inside the sun. The question is, how do we find it? Right? That's all of this technical thing in one line. All right. So this again, this idea, skip this, was the idea is also very well known. If the dark matter that is inside the sun, they annihilate, they produce neutrinos, you can detect those neutrinos on the Earth. Why neutrinos? Because nothing else will come out of the sun. Right? Everything else will get captured or will get stopped. Only neutrons will come out. Turns out, even neutrinos can get attenuated inside the sun because the sun is so dense. And most of the dark matter accumulates inside, like within 1% of the solar radius. Right? Okay, I'll be finishing in 2 minutes.
Okay,
No, no, it's just I have to go.
No,
That's
that's
okay.
okay.
Yeah. So this tells you the mean free path, which is about the solar radius, and then the idea is you can detect these neutrinos, and that's what we are doing. We are using the Super-Kamiokande experiment. There is an experiment in Japan, which is a water chain cup detector. It has a 50 kiloton, although 22 kiloton is used for science purposes. And yeah, this is the location in Japan. And this has, well, this first of all, it's a Nobel Prize-winning experiment, and it has been used to do a lot of things like proton decay. The best limits of proton decay come from Super K. Measurement of solar and atmospheric neutrinos. They discovered solar neutrinos. Well, they discovered solar neutrinos. They discovered atmospheric neutrino stations, more precisely. They discovered neutrino stations, that's for which they got the Nobel Prize. They measure atmospheric neutrinos. I'll tell you what that is. And they can also do a lot of new physics. Right? So here we are sort of doing a new physics scenario. Basically, what we are saying is this is the sun. The sun is producing some high energy neutrons because of dark matter, which is annihilating. These neutrons will go through the detector, put an angle, right? You see, and what you do is you look at the sun and you see whether there is an excess of events or not over backgrounds, right? So there are various event classes of event classes in super K. This is the angle cos theta sun. This is towards the sun, cos theta 1. That's how it's defined towards the sun. And these are the data points. The data points are coming from atmospheric neutrinos. And you see, none of they have excess, right? And this has been used to derive the very stringent limits, in fact, the world-leading limits on dark matter proton scattering by super K. What we are trying to do is we are using the same data set to search for dark matter electron scattering. The idea is the same. Again, dark matter gets captured, and it's to neutrinos, and you see the neutrinos, right? So this is one slide on atmospheric neutrinos. Atmospheric neutrinos are produced when cosmic rays interact with the atmosphere, produce neutrinos because of various particle physics processes. The important thing that we are emphasizing in this work is if you plot the neutrino energy versus the neutrino flux, these just consider on these red dots. These are atmospheric nu mu's, and these are atmospheric nu e's, the blue dots. So obviously, if you are searching for some new physics which has same amount of nu mu's and nu e's, searching for it in nu e's is better because the background is lower. This is a guaranteed background. Wherever you look at, the atmospheric neutrino is like 4 pi, right? If you look, there's that. So search using using nu e is much better, and that's what we are doing. So let's skip this thing. This is the last plot. This, as I said, this should come, as you can see. It really has to be very soon. Yeah. So this is the dark matter mass on the x-axis. This is dark matter electron scattering on the y-axis. This line that you see is coming from xenon 1 ton. So this is assuming dark matter gets captured inside the sun using electron scattering and then annihilates to nu bar, right? This line is from xenon 1 ton. That is, anything above is ruled out by xenon 1 ton experiment, now terrestrial experiment. There's some old results by Tarok and company where we were using ice cube and deep core to see the color. So that we were also ruling out new parameter space. And there's also old super result by Joachim Kopp where he was also ruling out some part of parameter space. What we are doing here is we are trying to use this super results, and our results are basically this shaded band, right? Depending on whether you use nu e or nu mu, nu e obviously gives a better result, as I explained, because the background is lower, we get a better result, right? And then we have some projection for Hyper-K. Hyper-K is the funded, under construction, next generation water jet rocket. This is what dark matter goes to nu bar. This is what dark matter goes to tau plus tau minus. And as we have, at least in the mass range of 4 to 200 GeV, we have the almost the leading constraints on dark matter electron scattering, provided you are in these modes. Right. So at the end, I hope I have been able to demonstrate that searching for beyond the standard model physics in cosmology and particle physics is exciting. And then these are okay, I'll stop since I'm already out of time. Thank you.
Thank you. It was a very comprehensive talk. So I'll open the floor for questions. Maybe should we take online first?
Take online.
Anyone online? Kieran? Okay, nothing online.
I wanted to ask, like, how much does the constraint depend on the velocity distribution of dark matter?
Oh, good.
I guess that's
yes.
Critical kind of.
Yes, good. So for xenon constraints, these really depend on velocity distribution. For these things, they will change by a factor of 2, not much. And that is simply because here your xenon is mostly sensitive to the highest energy dark matter particles. These are mostly sensitive to the lowest energy dark matter particles. The lowest energy particles will be more easily captured. They are slow, they'll be easily captured. So there is a complementary of which part of the velocity distribution you are in. So these limits will change by a factor of 2, 3 at most, not much. Yeah. And unlike terrestrial experiments, because there the spectrum is important. Here we don't have a spectrum. Right? So that's why it's here there is a bigger model dependence in the sense that not only we are having dark matter electron scattering, we should also annihilate to a certain level. That's a bigger constraint, right? And then we effectively something like the leptophilic dark matter, where we are mostly going to leptons. The other constraint that we can have here is if you annihilate to leptons, you must have couplings to protons by loops, by standard model loops, no new physics, right? And then that can put a constraint, but for certain couplings, mostly for axial couplings, the hadronic loops, the loops with hadrons will cancel. We do not contribute, at least to 2 loops. This has been shown in the literature.
Yeah, because here you are considering mainly that the main capture mechanism is with vectors.
Yes,
Yes,
correct. That's it.
Actually, my question was also about that because you induce scattering of
Correct.
protons, neutrons.
Yes, so it has been shown.
So does that include a running? So because there were some studies basically which basically looked at running down, they induce independent scattering.
Yes. So so that's a good. So just for everybody. So remember, so what Michael is asking is, well, we have a Lagrangian, right? And then from the Lagrangian you get the capture. But if you think of xenon, these are happening at the nuclear level, right? This Lagrangian is written at a high scale, right? You have to do, that's the running of the coupling. So those things we have just in our work, our sigma chi e is just a normalization parameter. So we have not done from a Lagrangian perspective. But if you're asking that when people are connecting this leptonic coupling to the hadronic coupling, do they include the running? I think the answer is no. I think. But yeah, you don't know.
I don't know.
Yeah. You can go to Melbourne.
So I know that people
You can go to Melbourne
look
and
at
ask.
running and so on.
Yeah, you know what you say is perfectly fine. Yeah.
But I mean, this is not. This is.
No.
I mean, will the running be very strong?
Yes.
So there can be very large effects.
Yes,
because if you have only spin dependent interaction,
If you only have spin dependent,
if you only
generate
spin independent.
and one loop, if you have spin dependent, that can overshoot your G levels.
That comes because if you take start from Lagrangian is the UV complete Lagrangian.
Right.
Once you go to nuclear level, that's where the running comes.
Sure. If your leading effect is spin dependent, then you have to probably look at the spin independent.
I think even other things people have, I think the papers I've seen, they have just taken some simplified models, Lagrangian models, and then
so Kirtiman and I and team we looked at this. I mean, at the different contexts, but those were more with colored mediators. I mean, you don't have colored mediators here. There the running was very strong.
Yes, I mean here for us sigma chi is just a normalization parameter. That's it, nothing else. And we're hoping somebody else will do the model building. To be honest.
Yeah, well, that's independent of it, right?
Yeah,
No, there is a model dependent. No, there is a model dependence. As I said,
So
some of
you choose some operator
which will switch off the hadronic couplings.
Yeah.
So that it's not induced.
I could not find.
Yeah. So you have to choose only those couplings for which hadronic cross sections are not large enough. Because hadronic cross sections are much stronger.
Yeah. To get something like minus 42.
Yeah, 47 something. Not at least. Yeah, 47 also.
Even if it were loop suppressed.
Yes, agree. Yeah. So that's where the biggest model dependencies come in here. Right? But as I said, I mean, people have shown that for, at least for some axial couplings, the hadronic things can run actually at least two loops they don't appear.
Else? Last chance online.
No, that's still 7.
I was asked,
Yes.
you may have said it, but I can't remember.
No, maybe I said it too fast.
How do we, like, we're detecting these neutrinos or leptons that are making it from the dark matter in the sun?
Yes.
How do we distinguish those neutrinos and leptons from just Stenimol processes?
Oh, sun is not emitting neutrinos at these energies. So we are talking of neutrinos at these energies, say somewhere here. So
I see.
sun is emitting, the solar neutrinos stop at around 10 MeV.
Right.
That's it, nothing.
Is that
So these are much higher energy neutrinos than solar neutrinos.
right? And they're coming. So your dark matter comes in, it scatters with an electron so that its energy is small enough to be able to capture the sun.
Yes.
And dark matter, you're saying, is annihilating.
Yes.
So then, does that put some sort of low limit on the mass of dark matter?
Yes,
Yeah,
correct.
is that right?
So yes, so that's a great question. So if you look at this plot, you see that this plot starts from about 4 GeV. That is because if the dark matter mass is less than 4 GeV, the electron is so energetic it will kick out the dark matter. The electron in the sun also, so this is technically called the evaporation mass. The electron also has some thermal motion. So the story is, let me repeat, the dark matter comes in, scatters the electrons, get captured inside the sun, and then it is scattering around. But if it's too light, the electrons will give enough momentum that will get out. Right? But it's heavy.
Right.
If it's heavy enough, it will get settled. So that's why this plot starts at 4 GeV. It's 4 or 5 GeV, something like that. There is a slight model dependence, but that model dependence, as far as I know, can do from 3 to 5 GeV, as far as I know.
I see. But then also the sort of the high energy neutrinos we're detecting at Earth, most of that energy must be coming from the mass of the dark matter.
Yes. So this is dark matter annihilation, right? So the Chi bar is going to nu bar. So the entire dark matter is getting putting into the neutrinos. So for a 100 GeV dark matter mass, so the neutrinos have an energy of about 100 GeV. And the sun is not emitting any 100 GeV neutrinos. That's it. That's why the only background is atmospheric neutrinos. I see. Right.
Anything else? If not,